This is Radio Ecoshock with Alex Smith.
Everybody knows when the permafrost thaws, greenhouse gases will go through the roof, forcing terrible global warming. Surprising new science says maybe, maybe not. A team of American and Canadian experts just published an important new study about permafrost thaw as the modern Arctic hits record heat. As always, the truth is weirder than we thought. Our guide is co-author Dr. Jeremy D. Shakun, Assistant Professor of Earth and Environmental Sciences at Boston College. From Boston, Jeremy Shakun, welcome to Radio Ecoshock.
Thanks, Alex. Good to be with you.
Jeremy, we have a few other problems right now, like will our society survive a deadly pandemic? Why should we care about what happens in the far north, where hardly anyone lives?
Well, one of the biggest reasons is because it contains tons of carbon. And when I say tons, I mean literally hundreds of tons of carbon. And so what happens up there won't necessarily stay up there. That carbon can come out of the ground, go into the atmosphere, and then drive climate change for all of us, anywhere you live.
I know that we should put ourselves on the geological clock, so to speak. When did 1/4 of the land in the northern hemisphere freeze up year-round?
So that's a good question, and that's actually a lot of what our research ties into, is trying to understand the past history of when so much of the North became cloaked in permanent freezing conditions. But as a first guess, it's probably reasonable to think it was about 3 million years ago when the Northern Hemisphere first descended into the Pleistocene ice ages.
And scientists need signs or proxies to figure out what the climate system was doing long before we had instruments. To understand the signal your team used, I think we all need a new word, and that is speleothem. Jeremy, what is that? What are they?
So, yeah, a speleostem is just a fancy word for any kind of mineral deposit that you see in a cave. So that's stalactites hanging from the ceiling, stalagmites coming up from the ground, flow stones, which are kind of the pretty, drapery formations you can see on the wall of a cave. All of those different deposits in a cave are referred to as speleothems.
So how can minerals dripping in a cave tell us whether land above was permanently frozen or thawed?
Well, that's the key thing, right, is for that to happen, you need there to be water dripping in a cave. And that's not going to happen if the ground is below the freezing point and there's no liquid water, right? So if you imagine going far to the north today in Alaska or something, somewhere where the ground is permafrost, where it's permanently frozen, there isn't any dripping or flowing water in those caves. Any water that's in there is solid ice. So in those places today, there are no speleothems being deposited. The cave is turned off.
So if you can get some of these rock samples, do you have to test them in situ, or do you bring them back to a lab? And then how do you figure out what the timing of when they formed is? How do you do that?
Yeah, exactly. So that was our approach, is as you said, to go into the cave and find some stalagmite that must have grown in the past when the ground was thawed and there was water dripping. So we can't analyze it in the cave. You can go look at a stalagmite in a cave and you have no idea. The thing could be 100 years old. It could be a million years old. And you're not going to be able to tell because it's so perfectly preserved underground, especially in a frozen cave, that visually you can't tell. So you got to get the thing out of there. You got to take it back to a lab. And then ultimately what we do is we extract really minute amounts of uranium, which is radioactive, from inside the speleothem, and we can figure out how much of that uranium has decayed away through time, and then basically backtrack how long ago did that speleothem form? When did that uranium clock in the speleothem start ticking?
Well, right, let's go back to a key paper published in the journal Nature in January 2020. A team led by the Israeli scientist Anton Vax examined speleothems, or cave drippings, in Siberia. Did those scientists actually travel to the caves in the Russian far north, or were they using speleothems already in a collection?
No, I think they actually traveled all the way up to Siberia and spent a lot of time in those caves and pulled out samples to date. And their study was really what triggered us to be interested in following up and doing a similar study. And the reason is because permafrost is so variable. For anybody who lives up in the Arctic, you know that you can be on one side of a hill where it's the south-facing side and the ground might be thawed, but you head over to the north-facing side and it's frozen. Likewise, across the whole landscape, permafrost, it can be very patchy and scattered. So you go look at one spot on the map to see when in the past it thawed, and you find out it did. What does that mean about the whole Arctic? How far can you extrapolate from one spot? And so that's what we thought when we saw this Siberian study from last year that you mentioned. We thought, those are really interesting results, what they're finding about the history there. But how far does that extend? And so that's why we wanted to really do a follow-up of the same approach going into caves. But we said, let's head over to Canada, look on the other side of the Arctic and see what's going on there.
The title of the paper led by VAX is Paleoclimate Evidence of Vulnerable Permafrost During Times of Low Sea Ice. We have very low sea ice now, so naturally this sounds important. What is the relationship, Jeremy, between disappearing sea ice and permafrost thaw?
Good question, and we don't totally know, but that was really the main headline finding from that VAX study last year, was they found that a lot of their speleothems grew 1.5 million years ago, 1 million years ago, 500,000 years ago, but thereafter, things just froze up. They didn't find any speleothems younger than 400,000 years ago. The cave just turned off. And we had the same result in Canada. So that looks kind of like an Arctic-wide phenomenon. The permafrost really stabilized over the last 400,000 years. Coincidentally, other researchers have taken a lot of ocean sediment cores from the Arctic and found out, what do you know? Right at that same time, 400,000 years ago, is when it looks like perennial, year-round sea ice cover first developed in the Arctic. So that was really the point of the VAX study, is to say, look at this. There's a clear connection going on. At the same time the permafrost firms up is also when the Arctic gets covered in year-round sea ice. So there's presumably some kind of connection. Now, to your question of what's the nature of that connection, how are these coupled? Well, we don't know for sure, but one possibility that the VAX team suggested is if you remove all that ice over the Arctic Ocean in the summertime, you can do two big things that can cause the permafrost to thaw. One of them is in summer. With all that open water up there, you can just have warmer summers, and that can bring more heat over the landscape and warm the ground up in the summertime. Then you head later in the season towards the fall and the winter, and without that sea ice cover, you can get more moisture evaporating off of the ocean and then dumping down as snow on the landscape. And that has a similar effect because the snow helps to insulate the ground underneath it during the winter. So it basically helps to keep the winter chill out from penetrating into the ground. So that also helps to promote ground warming and thaw. So that those two things, the summer part and the winter part, might be the links that help to have sea ice lows lead to permafrost thaw.
Well, we know from ice cores and other proxies that there have been interglacials, there have been warming periods during the last million years, but nothing really as hot as we're heading for right now. And yet your cave drippings show that the permafrost had indeed thawed above it during those times. And this is the shocker for me. Permafrost can thaw, and yet no big climate change happened. What do we know, Jeremy?
Well, yeah, so that's true. You're right. In the last million years, it was never a whole lot warmer than today, at least globally. But there probably were a couple of different interglacial periods in that time interval that were warmer than today, particularly maybe within the Arctic region. Not hugely warmer than today, but on the order of, degrees, something like where we're headed maybe in the middle of the century, later in this century. So we might be sort of approaching that mark not too far down the road. The other thing, I guess, going on here, though, is the point you brought up before about sea ice. There seems to be this connection between the history of permafrost stability and the history of when there's sea ice in the Arctic Ocean, and that removing that sea ice cover in the summer seems potentially like an important sort of release valve that then makes the permafrost more vulnerable to warming. So we still have a fair bit of sea ice in the Arctic. I mean, it's going fast. There's half as much now as there was when I was born 40 years ago, but there's still a fair bit up there. But as we lose more and more of it, if that sort of paleo connection we see hinted at in the geologic record holds, that might be making the permafrost more vulnerable to sort of the same level of warming.
Or there could be completely other factors like changes in ocean currents and things like that.
Absolutely. Yeah, it's not as simple as just sort of taking global temperature 500,000 years ago to comparing it to global temperature today, right? As you're bringing up, all sorts of local regional factors can be different between different time intervals. And so you always have to pay attention to those kind of regional dynamics of what's in play.
But surely, Jeremy, there must have been a lot of carbon locked up in the permafrost when it did thaw in those past ages. What happened to that?
Well, that's a good question. And, maybe not. I don't know how much permafrost was locked up there. There might have been, and that's kind of the picture we have today, right? Because there is such a huge amount of carbon in the permafrost. It's something like twice as much up there right now as we have in the atmosphere. But maybe maybe a million years ago, the permafrost had been thawing repeatedly over and over and over again. And if that was the case, then there might not have been such lengthy cold intervals for the permafrost to slowly accumulate more and more and more and more carbon getting churned down into the ground like we have today. So that is a possibility, that there weren't big carbon bursts simply because the ground just wasn't as clogged up with carbon as we're familiar with it today.
Why would the cycles of freezing and thawing stop? Why did polar regions, 400,000 years ago, stay so solid for so long? Do we know?
I don't think we totally know. But things do seem to have firmed up. I mean, there's you mentioned records from ice cores. We have records from over in Greenland that make it look like the Greenland ice sheet also probably was a little more twitchy before 400,000 years ago, and it also sort of has firmed up in the last few 100,000 years. Like I mentioned, the sea ice over the Arctic Ocean likewise seems to have firmed up in the last few 100,000 years. So there seems to be something that's gone on in the Arctic that's pushed it toward a little bit more of a permanently cold, stable, icy state in the last few 100,000 years. Why that is exactly, what's going on, how that involves the ocean or connections with the sea ice, the ice sheet, if these things are all linked together, I think those are big, outstanding questions. But I think we're getting more and more hints from the geologic record that really did happen. And so I think going forward, the question is to sort out why. How is that the case? And then, of course, what does that tell us about the future sensitivity of the region to warming?
This is Radio Ecoshock. I'm Alex Smith, looking into what happens as the northern lands release their stored carbon into the atmosphere. From the Department of Earth and Environmental Sciences at Boston College, our guest is Dr. Jeremy Shakun. So, Jeremy, where are we now in the process of permafrost thaw? Are the drippings starting to happen again in the caves?
In some of our caves, they absolutely are. Yeah. I was in one not last summer, but the one before, in the Southern Rockies down in Alberta, and it was July, and there was plenty of dripping. You could see actually just holes in the ice on the cave floor just getting drilled into from drips overhead. Just speaking to folks who lived in the town down below the cave, they said, "Oh yeah, we used to go into that when we were kids in the '70s, and it was just filled with so much more ice. But now it's thawing out." So that's certainly true in some of these caves, especially on the southern fringes of the permafrost. When you head all the way up to the far north in the northern Yukon, I think those are still rock solid. That's an area that is, deep in the core of the continuous permafrost, where things are still just too solidly below the freezing point to yet be thawing out.
I recently interviewed the Danish scientist Sune Rasmussen about their team's work analyzing Greenland ice cores, and they analyzed abrupt warming events in Greenland and the North Atlantic called Danskard Oskar events, or DO, and they cross-referenced their with speleothems, as you mentioned, but I don't see that cross-check in your recent paper. Do ice cores and speleothems agree on when warmings occurred?
Well, I guess it's sort of a question of time scale. So, those DO events you mentioned, the heart of those DO events are just within the last ice age. So 30,000, 60,000 years ago. So there's a lot of work comparing speleothems around the world to the ice cores during those DO events of the last ice age. And there they agree beautifully. Here, we're looking really at much longer time scales. We're looking at when speleothems were growing in the far North Arctic, going out 1.5 million years. So that's really getting at longer sort of, a million-year kind of time scales compared to those shorter, what we would call millennial or sort of 1,000-year century kind of time scales.
Well, sometime within the last 80,000 years, Greenland and the North Atlantic warmed at least 10 degrees hotter than they were within a matter of decades. And yet, it doesn't look like the speleothems started to function again or the permafrost thaw. There must be a tremendous time lag between when the warming happens on the surface and when the land really begins to give up that frozen nature.
Yeah. So two things to say on that. That's right. I mean, one thing with those DO events is they're happening during an ice age. So that's within the last glacial period. So you're right. North Atlantic temperatures are jumping 10 degrees, 15 degrees Celsius in a few decades. But they're starting from much colder temperatures than today. So I think that's part of why we wouldn't see a permafrost response to that. But you're right. There is going to be a time lag. I mean, a lot of our caves, they're deep. They're down tens of meters below the surface. So that's not the kind of thing you're going to warm up in one season or in 10 years necessarily. That could take quite a bit of time for that heat to really propagate all the way down through the ground and warm things up.
And humans are now causing a warming many times faster than any natural force that we know of. Is it possible previous thaws recorded by the growth in the caves developed so gradually that any CO2 or methane releases were just sucked up by other natural systems?
Yeah, absolutely. So back to that riddle of, we seem to have this pretty clear evidence from the caves in Canada and the Siberian caves from the VAX study that the permafrost did thaw in a big way in the past, and yet we don't see big spikes in CO2 levels in the atmosphere from our other proxy records. So to that riddle of why not, a lot of it could be timescale. We're used to thinking about, the Arctic is warming, this carbon's going to come burping out of the permafrost, it's going to clog up in the atmosphere and cause a lot of warming. But we're always thinking about decades, right? I mean, maybe a century or two. That's very quick from the perspective of the Earth system. So it might just be that a lot of these paleo events we're looking at, they're slower. The thawing events are happening over many centuries, or maybe more likely over many thousands of years. And if that's the case, that's a slow enough dribble of carbon to the atmosphere. It could go elsewhere in the Earth system. That's enough time that a lot of it could dissolve into the ocean. It's enough time that it could get taken up by vegetation or growing elsewhere on the planet. So that might explain the gap.
Well, this new science seems to offer some hope, but there's also a possible dangerous twist as well. What is the concern about carbon being built up over the long freeze of 400,000 years we just had?
Well, that's right. So, yeah, I mean, if these results are right, then the permafrost hasn't been as dynamic in the last few 100,000 years. It's been solid, and it's been able to then accumulate more and more carbon through time that it hasn't released through thaw events. So, kind of ironically, those cold conditions for the last few 100,000 years have maybe just allowed the permafrost to get more and more filled up with frozen carbon that we are now sitting on and probably beginning to disturb more and more and potentially, admitting to the atmosphere through thaw.
I am concerned a tiny but persistent group of climate deniers will take your new study and science advances and say, see, permafrost can thaw and nothing happens to the atmosphere. Don't listen to those climate alarmists. And your response, Jeremy, would be?
I think my response would be, these are different, right? This is, again, as we just said, we're comparing past events to what's going on in the future. So we always have to be careful to link too quickly from, the one to the other. Things can be very different. For instance, the time scale can be different. So we need to understand why things happen the way they happened in the past. We don't just want to look and see, this didn't happen, therefore it won't happen again in the future. We need to understand the mechanisms, the processes involved. So if they said that, I'd say, whoa, slow down. You're being way too quick to jump to conclusions. I don't think we can say that at all at this point. And I think the main thing I take from the study, honestly, is we thought that these cave formations were going to be old. I mean, really old, much, much older. We thought that these were probably going to be several million years old. You'd have to go back to times in Earth history when things were just substantially warmer than today. But they weren't. A lot of them turned out to be in the last million years, which, like you said, was not a whole lot warmer than today. That's the part that caught me off guard. I didn't expect to find that. I thought that, well, that's not going to be warm enough to have thawed out the frozen north. And yet, apparently it was.
And in the end, what do we do with the millions of people who are worried that permafrost will thaw and really cook us here on Earth? What does your study say to us?
Well, I think the only really solid way we're going to keep the permafrost from thawing is by stopping temperatures from continuing to rise. So if we want that to happen, you know the story there. That comes down to reducing emissions and ultimately trying to stabilize the climate system so that things don't run too much further along.
So maybe not try it and see what happens. Instead, we've got to take some preventative action. From the Department of Earth and Environmental Sciences at Boston College, we've been speaking with Dr. Jeremy Shakun. He is co-author of the new paper, Increasing Pleistocene Permafrost Persistence and Carbon Cycle Conundrums, inferred from Canadian speleothems. That was published in Science Advances on April 28, 2021. You can find links to follow up, as always, in my show blog at ecoshock.org. I'm Alex Smith, reporting.